Hello everyone, welcome back to my channel. So in this video we'll going to learn about a new series, that is Laurent series. Okay, in complex number series, in complex numbers topic. Okay, so if you're first time to my channel, please consider subscribing and encourage me to do more videos like this. Right, so Laurent series, if f of z is, the statement of Laurent series is like this: if f of z is analytic at every point within and on a ring shaped region, okay, so bounded by two concentric circles. Okay, so two concentric circles, if it is bounded by two concentric circles C1 and C2, so this is C1 and this is C2. So this is C2 and this is C1 with radius R1 and R2 respectively. So this is R2 and this is R1, so that R2 is less than R1. Okay, and for every point Z within R, so for every point Z within R, within this concentric circle ring, right, so f of z can be represented as power series. F of z can be represented as a power series, both positive and negative. Okay, so the difference between Taylor series and Laurent series is, in Laurent series also we are doing the expansion, but we are doing the expansion only for positive powers of z minus z naught. So you will get z minus z naught whole square by 2 factorial plus of course f double dash of z naught for second, so f of z naught plus z minus z naught by 1 factorial into f dash of z naught plus z minus z naught whole cube by 3 factorial into f triple dash of z naught, and so on. Right, we are getting only positive powers of z naught. Okay, because there we are considering only one circle, that is one circle only you are going to consider, and if the point lies inside the circle, then you can easily find the expansion. Okay, but now when you are considering two circles, like this, then we can expand that in both positive powers like this and negative powers like this. Okay, so simply this is the Laurent series expansion formula, where an and bn are the coefficients of the Laurent series, which is given by these formulas. An is equal to 1 by 2 pi I, it is integrated over circle C1, and bn is integrated over circle C2. Okay, so that means inner circle will gives you the negative powers and outer circle will gives you the positive powers of in the expansion about z is equal to z naught. Okay, so this negative powers is called as principal part of the Laurent series expansion, and this positive powers is called as analytic part of the Laurent series expansion. Okay, so there are two concentric circles whose radius are R1 and R2, and its ROC is given by R2 less than, this is R1, so R2 less than z minus z naught is less than R1. Okay, so there will be some considerations to be considered in the Laurent series expansion based on the given ROC. Okay, so that we'll see while we are doing problems. Okay, so this is about Laurent series, and this is the formula you have to remember for Laurent series. Okay, bn by z minus z naught, so you have to keep this in mind, principal part. Okay, so we have already seen that based on principal part of the Laurent series expansion, we have classified the singularities. Okay, isolated singularity, removable singularity. Okay, so it is that is based on that classification is based on this principal part only. Okay, now we'll see some problems based on this Laurent series. Okay, simple in explanation. So this is the Laurent series expansion formula. So let us see a problem on Laurent series. Okay, So expand e power 2z by z minus 1 whole cube about z is equal to 1. So you have given with f of z is equal to e power 2z by z minus 1 whole cube, and z is equal to z naught. So this z naught is equal to, so z naught value is 1. Okay, so if you have f of z is equal to e power 2z by z minus 1 whole cube, so you are finding about z is equal to 1, so z minus 1 is equal to p. Let z minus 1 is equal to p, so z becomes now p plus 1. So then what will be f of z? What will be f of z? E power 2 into z is there. So what is z? Z is equal to p plus 1 divided by z minus 1 is p, so it is p cube. So this is of the form a power m plus n is equal to a power m into a power n. So e power 2p into e power 2 divided by p cube. So e power 2 divided by p cube. So what is e power x expansion? So 1 by x plus 1 by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus so on. So now in the place of x you have 2p, so x is equal to 2p now we have. So I am writing the expansion of e power 2p, so that will be 1 by 1 plus 2p by 1 factorial plus 2p whole square by 2 factorial plus 2p whole cube by 3 factorial plus 2p whole to the power of 4 by 4 factorial plus 2p whole to the power of 5 by 5 factorial plus so on. Okay, so e power 2 into, send this p cube also inside, so 1 plus 2 by 1 factorial is 2 only, p into 1 plus p cube is p square, so it will be 2 by p square plus this is 2 square by 2 factorial is 2 only, and p square into 1 by p cube is by p, plus this will be 8, this will be 6, 8 by 6 is 4 by 3. This p cube and this p cube gets cancelled off. Okay, this and this gets cancelled off, right? Plus what will be this? 2 power 4, 16 by 24, 16 by 24, 4 4s are 4 6 as this, 2 by 3 will get 2 by 3 into, so this is p to the power of 4, p to the power of 4 into 1 by p cube is p, right? Plus 2 to the power of 5, that is 32 divided by 120 you will get 32 divided by 120, 4 8s are 430, 2 4s are 215, so 4 by 15 into, so this is p to the power of 5 multiplied by 1 by p cube becomes p square, right? Plus so on. So what is p again? P is equal to z minus 1. So if you have e power 2 into 1 plus 2 by, sorry, this 1 when multiplied by p cube it will be 1 by p cube, very sorry, so it will be 1 by p cube, that is z minus 1 whole cube. I'm sorry here, so I have done mistake. So 1 multiplied by p cube is 1 by p cube plus 2 by z minus 1 whole square. Okay, so in the place of p I am substituting with z minus 1 plus 2 by z minus 1 plus 4 by 3 plus 2 by 3 into z minus 1 plus 4 by 15 into z minus 1 whole square plus so on. Okay, so this is the expansion of f of z in about z is equal to 1 using Laurent series. So if you observe, you have both positive, so you are expanding about z is equal to 1, so you'll get z minus 1 terms. So in Laurent series you'll get both positive and negative values, negative powers of z minus 1. So all these represents positive powers of z minus 1, that is all these are analytic part, right? So this is DC anyhow, this is DC, right? So all these represents the analytic part. So all these three terms represents the principal part. These three terms represents the principal part. So we have learned in singularities concept, while I am dealing with singularities concept, I have told you a concept called pole. Okay, so what is pole? Pole represents if the principal part contains finite number of terms, that is from 0 to, that is from 1 to m. if you have 1 to m. Okay, so 1 to m, then z is equal to z0 is said to be pole of order m. Pole of order m. So now we have the powers. This is power 1, this is power 2, and this is power 3. So now we have negative powers of finite value. So total number of negative powers is only finite, that is from 1 to 3. Yes or no? So only we have the powers from 1 to 3. So that is why z is equal to 1 is said to be pole of order 3. Pole of order 3. So from this also we can say that this is said to be pole of order 3. So it is equal to 1 is pole of order 3. Okay, so from the f of z, that is from the function, you can directly say that is z is equal to 1 is a pole of order 3, and this is how you can prove from Laurent series also. This is from Laurent series also we can prove the same, that z is equal to 1 is a pole of order 3, because we are getting finite values or finite terms for principal part. There are finite terms for principal part, and that finite terms is 3 in number. Therefore z is equal to 1 is a pole of order 3. Okay, so this is the conceptual study. Okay.